For most of human history, when a comet crossed the sky, people believed it was a warning, a burning message from something larger than themselves, a sign that something had shifted in the order of things, far above their heads, in a place they could not name or reach. They were not entirely wrong. They just did not know how far away the message was sent from. A comet, when it crosses our sky, has been traveling for a very long time. It has come from somewhere we cannot see. It has spent thousands of years, sometimes millions, drifting in a place so dark and so distant that no human instrument has ever directly observed it. By the time we see its light, the comet is already on its way back. It will not stop. It will not return for centuries, if it returns at all. For most of human history, when our ancestors watched these strange travelers cross the sky, they were looking at the smallest fraction of something much, much larger. We are going to talk about that larger thing tonight. Right now, without knowing it, you are inside something vast, something invisible. It begins where the planets end. It does not stop until you are halfway to the nearest star. It contains trillions of objects, each one silent, each one frozen, each one older than the Earth. No telescope has ever photographed it. No spacecraft has ever reached it. We cannot see it, and yet we are completely certain it is there. This is the Oort Cloud, and you have been living inside it your entire life. Settle in, slow your breathing. We are going to take this slowly, the way the Oort Cloud itself moves, which is to say, barely at all. We are going to walk all the way to its inner edge, then all the way to its outer edge. Then we are going to ask what it means to live inside something that cannot be seen and cannot be reached and cannot be measured directly. And then, near the end, we are going to watch it slowly come apart. Billions of years from now, when the sun has finished its long burn and the last of its grip lets go. There is no rush. The Oort Cloud has been there for 4.5 billion years. It will still be there when you wake up tomorrow. Let us begin. Comets are old, older than language, older than the cities and the stories and the names we have given to the things in our sky. Whenever an ancient civilization kept records of what they saw above them, comets were there, somewhere in the records, written down with care. Babylonian astronomers tracked them. Chinese astronomers tracked them with extraordinary precision, keeping continuous records of comet sightings for more than 2,000 years. Greek philosophers argued about them. Aristotle thought they were atmospheric phenomena, something happening in the upper air, like the weather. He was wrong, but the idea stuck for 2,000 years. In every culture that watched the sky, comets caused unease. They did not belong to the regular rhythm of the heavens. The sun rose and set, the moon waxed and waned. The stars wheeled overhead in their predictable year-long pattern. The planets moved against the stars in their own slow and graceful dance. All of these things were knowable. All of them could be counted, predicted, anticipated. Comets were different. They appeared without warning. They blazed across the sky for weeks or months and then vanished. They did not return on any schedule that anyone could detect. Each one was, by all appearances, a single event, a visitor from nowhere, going nowhere, leaving nothing behind but a memory and, sometimes, a fear that something important had been disturbed in the order of things. There is something deeply human in the response. To see a thing in the sky that was not there yesterday and that may not be there tomorrow, and to feel, almost reflexively, that this means something, that this is a message, that the universe is, in some sense, watching us and trying to tell us something we are not yet equipped to hear. The records that survive from antiquity show the same pattern in every culture, from China to Mesopotamia to Greece to the Americas. A comet appears. People notice. People worry. People try to figure out what the comet is for. The fact that comets often appeared near important events, the deaths of rulers, the outbreaks of wars, the changes in dynasties, was, of course, an artifact of selective memory. There were many comets in any given century, and many important events. The pairing of the two was inevitable, but once paired, the connection was hard to break. A comet, in the ancient mind, was a sign, and signs had to be read. Most cultures interpreted them as warnings. The Romans saw the Great Comet of 44 BCE, just months after the assassination of Julius Caesar, and decided it was the soul of the dictator ascending to the heavens. The Bayeux Tapestry, woven in the 11th century, shows the comet of 1066 hanging in the sky above the army of King Harold, who would lose the Battle of Hastings to William the Conqueror weeks later. In China, comets were called broom stars because they were thought to sweep evil from the heavens, or sometimes to sweep prosperity away with it. The Aztecs recorded a great comet in the years before the arrival of Cortés in 1519. They took it as an omen of disaster. They were not entirely wrong. The arrival of the Spanish would, within a few decades, destroy their civilization. The comet did not cause this, but the association was strong enough that, for the survivors, the comet became a marker of the moment when everything began to change. The fear was understandable. A comet is, after all, a thing that suddenly is, where nothing was before. Its light is real, its tail is long, it hangs in the sky for weeks. It does not look like an atmospheric event, no matter what Aristotle said. It looks like a piece of the deep sky, behaving in ways the rest of the sky never does. But the comets, the ones the ancients feared, came from somewhere. Each one had a history. Each one had been traveling for centuries or millennia before it was seen. And the place each one came from was not, as the ancients sometimes imagined, just beyond the dome of the sky. It was much, much further than that. In 1682, an English astronomer named Edmund Halley observed a bright comet crossing the sky. He was 26 years old. He had recently published the first comprehensive catalogue of Southern Hemisphere stars to work he had done from a small observatory on the island of St. Helena. He was a man of his time, scientifically curious, mathematically gifted, fascinated by the patterns that the sky might be hiding. When Halley watched the comet of 1682, something occurred to him. He had read older records of bright comets, the kinds of sightings that had been carefully documented across centuries. The comet he was watching looked similar in its path and brightness to comets that had been observed in 1531 and in 1607, roughly 75 years apart in each case. What if, he wondered, they were the same comet? The idea was, at the time, almost heretical. Comets were not supposed to return. They were singular events. Each one was its own thing, appearing once, vanishing forever. The idea that a comet might be orbiting the sun like a planet, but on a much longer and more elongated path, was new. It contradicted centuries of belief about what comets actually were. Halley applied the new mathematics of Isaac Newton, who was at the time his friend and collaborator. Newton's laws of gravity, only recently published, predicted that any object bound to the sun by gravity must follow an ellipse. The planets followed nearly circular ellipses. A comet, if Halley's idea was right, would follow a long, stretched-out ellipse, spending most of its time far from the sun and only swinging close occasionally. He worked the calculations carefully. He predicted that the comet of 1682 would return in 1758, give or take a year. he did not live to see it. Halley died in 1742 at the age of 85. 16 years later, on Christmas night of 1758, a German farmer and amateur astronomer named Johann Palitzsch pointed his telescope at the sky and saw exactly where Halley had predicted the comet returning. It is now called Halley's Comet. It returns every 76 years, give or take. The last time it appeared was in 1986. The next time will be in 2061. The mathematics worked. Newton was right. Halley was right. The comet was bound to the sun on an enormous, slow, predictable orbit, and it would come back and back and back again, as long as the sun was there to hold it. The success was, in its own way, one of the most important moments in the history of astronomy. It proved that comets, those mysterious visitors that had haunted human imagination for thousands of years, were not random events. They were not omens. They were not warnings from the heavens. They were physical objects, governed by physical laws on predictable orbits. The same mathematics that described the motion of the planets also described the motion of comets. The universe, even at its strangest and most apparently chaotic, was understandable. Halley's Comet has now been traced backward through history with the help of those careful ancient records. Chinese astronomers, Babylonian astronomers, European chroniclers, all of them had recorded its appearances without knowing they were watching the same object return. Its earliest recorded sighting was in the year 240 BCE. It has been making its slow, eccentric journey around the sun, give or take some small perturbations, for at least that long, probably much longer. When Halley's Comet returned in 1066, the year of the Battle of Hastings, it was the same object that had appeared in 12 BCE, just before the death of the Roman general Marcus Vipsanius Agrippa. The same object that had appeared in the year of the destruction of Jerusalem by the Romans in 70 CE. The same object that had been seen, presumably without being recorded, by humans across many continents and many centuries, each generation watching it cross the sky and wondering what it meant. It is, in this sense, the most patient companion our species has ever had. It does not know we exist. It does not care. It is simply on its orbit, doing what gravity tells it to do, swinging close every 76 years to wave at whatever civilization happens to be watching at the time. But the success of Halley's prediction opened up a much larger and stranger question. Halley's Comet was one comet on one orbit that had been observed many times. What about all the others? Astronomers began to catalogue comets carefully, recording their paths through the sky, calculating their orbits. They found, over the next 2 centuries, that comets came in 2 kinds. Some comets had relatively short orbits. They returned every few years, or every few decades, or every century or 2. Halley's Comet was one of these. Its orbit took it out to a maximum distance of about 35 astronomical units, roughly the orbit of Neptune. It was a member of what astronomers now call the short-period comets. These were eventually traced to the Kuiper Belt, a broad disk of icy bodies that surrounds our solar system just beyond Neptune. Every short-period comet was a Kuiper Belt object that had been knocked inward by gravity, falling into a smaller orbit that brought it close to the Sun. But the other comets were different. They had orbits so long that they had only ever been observed once in the entire history of human observation. They came from every direction. Some came from above the plane of the planets. Some came from below. Some came from directly opposite the direction of the sun's motion through the galaxy. They were not concentrated in any one part of the sky. They appeared, took their photographs, and left. They were the long-period comets. and nobody could figure out where they were coming from. In 1950, a Dutch astronomer named Jan Oort published a paper that would change how we thought about the structure of the solar system. Oort was, at the time, one of the most respected astronomers in the world. He had spent his career studying the structure and motion of the Milky Way galaxy. He had been instrumental in establishing that our galaxy rotates, that the Sun is not at the center, that we are part of a vast spinning disk of stars. His mind was tuned to the geometry of large systems, to the way gravity organizes things on scales, much bigger than the solar system itself. In the late 1940s, Oort began looking at the orbits of long-period comets. There were, by then, enough of them catalogued that statistical patterns could be analyzed. He looked at the directions they came from, the energies of their orbits, the way they distributed themselves across the sky. What he found was strange. The long-period comets were not random. They were not coming from one specific direction or from a flat disk like the planets. They were coming from a roughly spherical distribution centered on the Sun. They were coming from every direction equally, above the plane and below it, from the left and from the right. The sphere they came from had to be enormous. Oort calculated that the comets were coming from a region roughly 50,000 astronomical units away from the Sun. 50,000 astronomical units. To give that number some meaning, 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. So 50,000 astronomical units is roughly 4.5 trillion miles. Far enough away that light, the fastest thing in the universe, takes about 8 months to travel from there to here. And there had to be a lot of them. Oort estimated, based on how often comets fell inward and how long they would survive once they did, that there must be trillions of objects in this shell, trillions of comets, drifting in a vast spherical envelope around the entire solar system, each one preserved in deep freeze, occasionally disturbed enough to fall toward the Sun. Oort did not directly observe any of these objects. None of them. There was no telescope in 1950 that could see them, and there is no telescope today that can see most of them. He had only the indirect evidence of the comets that had fallen inward. From their paths, he inferred the existence of an enormous reservoir of ice surrounding everything we knew, hiding in plain sight. He announced the existence of 1 trillion objects no one had ever seen. He was right, probably. The hypothesis that bears his name today, the Oort Cloud, is one of the strangest scientific discoveries of the 20th century. It is universally accepted. Every astronomy textbook describes it. Every model of the solar system includes it. It is taught to first-year astronomy students as established fact. And yet, in the 76 years since Oort published his paper, we have not directly observed a single object within the main body of the cloud, not one. We found it the way you find a room in the dark, not by seeing it, but by feeling where it ended. There is something worth pausing over here, because it is genuinely strange. The Oort Cloud is the largest single structure in our solar system. By volume, it dwarfs everything else. The orbits of all the planets fit inside a tiny region, smaller than 1% of the cloud's diameter. The Kuiper Belt, where Pluto lives, is the next ring out. But even that occupies a vanishingly small fraction of the volume that the Oort Cloud takes up. The cloud extends from where the planets end all the way to roughly halfway to the nearest star. It is the most numerous population of objects in the solar system. Estimates of the number of objects in the cloud range from 100 billion to more than 2 trillion. For comparison, the entire Milky Way galaxy contains about 200 billion stars. The Oort Cloud may contain as many or more comets than the galaxy contains stars. Every one of those comets is its own small, frozen world hanging quietly in the dark. and we have never seen it. Every other major component of the solar system has been photographed. The planets have been visited by spacecraft. The sun has been observed by countless instruments. The moons have been mapped. Asteroids have been catalogued, named, and in some cases landed on. The Kuiper Belt has been studied by New Horizons, which photographed Pluto in 2015 and Arrokoth in 2019. But the Oort Cloud, the largest structure in our solar system, the home of trillions of ancient ice bodies, has never been directly observed. Not one of its objects has been imaged in its native location. Everything we know about it, we know from inference, from the comets that have fallen inward, and the orbits they followed when they did. The first plausibly direct evidence of an Oort Cloud object did not come until 2003, when astronomers discovered Sedna, a small dwarf planet on an enormously elongated orbit. Sedna may, depending on which model you believe, be a member of the inner Oort Cloud. It is the closest we have ever come to seeing one of the cloud's residents in its proper home. We will talk about it more in the next chapter. But Sedna is borderline. Most astronomers consider it to be on the boundary between the scattered disk, a region beyond the Kuiper Belt, and the inner Oort Cloud. It might be an Oort Cloud object. It might be something else. The categories blur out there, where the light from the sun is so weak that it is barely brighter than the brightest stars. So we have a structure that we are sure exists, that we have built an entire branch of astronomy around, and that we have never directly seen. Nobody on Earth has ever taken a photograph of the Oort Cloud. Nobody ever will, probably. Not in any of our lifetimes. The objects are too small, too dark, too cold, too far away. They emit no light of their own. They reflect almost none. They drift in a region where the sun is just one more star, a particularly bright one, but not bright enough to illuminate a comet 2 light months away. The Oort Cloud is, in a strange way, a triumph of human reasoning. We worked it out from gravity, from mathematics, from the patient observation of a few thousand comets falling inward across centuries of history. We assembled a picture of something that, by all sensible measures, we should not be able to see at all. And the picture is enormous. Before we walk out to the Oort Cloud, we need to remember where we are starting from. The Earth is 93 million miles from the Sun. That distance is called 1 astronomical unit. It is the standard yardstick for the solar system. When astronomers talk about distances in our cosmic neighborhood, they almost always use astronomical units, because miles or kilometers become impractical very quickly. Mercury, the closest planet to the Sun, orbits at about 0.4 astronomical units. Venus orbits at about 0.7. Mars at 1.5. The asteroid belt sits between Mars and Jupiter at roughly 2 to 3 astronomical units. Jupiter, the largest planet, orbits at about 5 astronomical units, 5 times as far from the Sun as the Earth is. Sunlight, by the time it reaches Jupiter, is 25 times dimmer than it is here. The Sun from Jupiter looks like a bright star, not a disk. You can still see it. You can still feel its warmth faintly, but it has lost most of its power. Saturn, the second largest planet, orbits at about 10 astronomical units, twice as far from the Sun as Jupiter. Sunlight there is 100 times dimmer than on Earth. Uranus is at 19 astronomical units. Neptune is at 30. By the time you reach Neptune, the Sun is just a particularly bright star, and the temperature of any object in direct sunlight is well below -300 degrees Fahrenheit. Cold enough that nitrogen, the gas that makes up most of Earth's atmosphere, would freeze solid if there were any of it around. Beyond Neptune, we enter the Kuiper Belt, It is a broad, flat ring of icy bodies, extending from roughly 30 astronomical units to about 50 astronomical units. Pluto, the most famous resident, orbits at an average distance of about 40 astronomical units, though its orbit is so elongated that it sometimes comes closer to the Sun than Neptune does. The Kuiper Belt is where most of the short-period comets come from, the ones with orbits less than 200 years long. It contains many thousands of small, icy objects, some of them quite large, like Pluto and its companion Charon, or like Eris, a dwarf planet about the same size as Pluto. At 50 astronomical units, we are at the outer edge of the Kuiper Belt. We are at the edge of what most people would call the solar system. The planets and the major rings of small bodies are all behind us now. Ahead of us is a region that, for a long time, was assumed to be mostly empty. It is not empty, but the things in it are very, very far apart. In 2003, a team of astronomers led by Mike Brown at the California Institute of Technology discovered a new dwarf planet. They named it Sedna, after the Inuit goddess of the sea who lives in the deep cold ocean and is associated with the spirits of the dead. Sedna is small. Its diameter is roughly 600 miles, about the size of a US state like Utah. It is reddish, possibly the reddest object in the solar system, colored by the same hydrocarbon haze that paints Pluto and Arrokoth. It moves slowly, because it is far away. But what makes Sedna interesting is its orbit. Most dwarf planets in the outer solar system have orbits that, while elongated, stay roughly within the Kuiper Belt. They might go a bit further out than 50 astronomical units at their farthest point, but they always come back eventually to roughly the same region. Sedna does not. At its closest point to the Sun, called its perihelion, Sedna is at 76 astronomical units, already further than any Kuiper Belt object goes at its closest approach. At its farthest point, its aphelion, Sedna is at 937 astronomical units, almost 1,000 astronomical units from the Sun. For comparison, that is nearly 20 times further out than the outer edge of the Kuiper Belt. It is almost a tenth of the way to the inner edge of the Oort Cloud. Sedna spends most of its orbit at distances where no other major object has ever been observed. Sedna's orbital period is roughly 11,400 years. It takes Sedna 11,400 Earth years to complete one trip around the Sun. The last time Sedna was at its closest point to the Sun, humans were just beginning to settle into the agricultural revolution. They had not yet built cities. They had not yet invented writing. They were learning for the first time how to grow grain and keep livestock. By the time Sedna completes its current orbit, who knows what we will be doing or if we will be here at all? How did Sedna get into such a strange orbit? Nobody knows. The leading hypotheses involve gravitational interactions with the inner Oort Cloud, with passing stars in the early history of the solar system, or with hypothetical larger planets that may exist in the outer solar system. Some astronomers believe Sedna is the closest member of what they call the inner Oort Cloud, or the Hills Cloud, named after the same Jack Hills who proposed hypervelocity stars. The inner Oort Cloud, if it exists, is a denser, more disk-like region that sits between roughly 2,000 and 20,000 astronomical units from the Sun. It is thought to be populated by objects whose orbits never bring them inward enough to be observed easily, but which sometimes get disturbed and become long-period comets. Sedna is, in this picture, the innermost ambassador of the inner Oort Cloud, the closest object we have managed to see, the first hint of the much larger structure that lies beyond it. A few other objects have since been discovered with similar properties. Most are smaller than Sedna and harder to see. They are sometimes called the sednoids, a small population of icy bodies on extremely elongated orbits that take them far beyond the Kuiper belt. There is 2012 VP 113, nicknamed Biden, discovered in 2014, with an aphelion of more than 450 astronomical units. There is Lelea Kohonua, discovered in 2018, with an even more extreme orbit. There are perhaps a dozen sednoids known today, and the population is probably much larger, with most members too dim to detect with current instruments. Each one is precious. Each one is a single data point telling us something about a region we cannot otherwise reach. Each one is the closest thing we have to a direct observation of the inner Oort Cloud, and each one raises questions we cannot yet answer. Why are their orbits clustered in certain directions? Some astronomers have argued that the alignment is statistically significant, that it suggests the presence of a large, undiscovered planet in the outer solar system. This hypothetical planet, sometimes called Planet 9, would be massive enough to shape the orbits of distant objects. The evidence is suggestive. The hypothesis remains unproven. Decades of searching with our best telescopes have not yet found such a planet, if it exists at all. The sednoids may be telling us something about the outer solar system that we have not fully understood. Or their orbits may be the result of selection effects, the fact that we can only see them at certain points in their orbits. We do not know yet. The questions are open, and the dataset is small. But what we do know is this: Sedna and the other sednoids are the only objects from the inner Oort Cloud, or anything close to it, that we have ever directly observed. They are the visible tip of an enormous and otherwise hidden population. They are the closest we have come to seeing the cloud's residents in their actual homes. If Sedna's farthest point is at almost 1,000 astronomical units, the inner Oort Cloud begins, roughly, where Sedna's orbit takes it, around 2,000 astronomical units from the Sun. That is roughly 40 times further out than the outer edge of the Kuiper belt, 40 times further than Pluto's average distance from the Sun. So far away that sunlight, by the time it reaches that distance, has dimmed by a factor of more than 400 million from what we experience on Earth. The Sun, from 2,000 astronomical units, is still the brightest object in the sky, but it is bright in the way that the brightest star in the night sky is bright. It is no longer a sun. It is a point of light. You could not feel its warmth. You could not see its disk. The inner Oort Cloud extends from roughly 2,000 astronomical units to about 20,000 astronomical units, 10,000 times further from the Sun than the Earth is. And then we reach the outer Oort Cloud. The outer Oort Cloud is the main body of the structure. It extends from 20,000 astronomical units to roughly 100,000 astronomical units. Some models suggest it may extend as far as 200,000 astronomical units, which is nearly halfway to Alpha Centauri, the nearest star system to our own. Alpha Centauri is about 4.3 light-years away, which works out to roughly 270,000 astronomical units. The outer reaches of our Oort Cloud may already be halfway there. To put that in distance terms, a human brain can almost grasp the outer edge of the Oort Cloud at 100,000 astronomical units is roughly 9.3 trillion miles from the Sun. 9.3 trillion. A million millions multiplied by 9. The kind of number where the units almost stop having meaning. You cannot picture 9.3 trillion miles. Nobody can. You can only know it is large. Light, the fastest thing in the universe, takes about 1.6 years to travel from the Sun to the outer edge of the Oort Cloud. So when you look at the outer Oort Cloud, you are looking at light that left the Sun more than a year and a half ago. The cloud is so far out that it is closer, in light travel terms, to the nearest stars than it is to the Sun. The Oort Cloud is not just a structure within our solar system. It is, in many ways, the structure that defines where our solar system ends. The Sun's gravity is what holds the cloud together. At the outer edge, the Sun's gravitational pull is so weak that it is barely stronger than the pull of nearby stars and the broader pull of the Milky Way galaxy itself. Any object out there is only loosely bound, a small nudge from a passing star or from the slow tide of the galaxy can be enough to push an object loose or to send it falling inward. The objects in the Oort Cloud are, as far as we can tell, all variations on the same theme. They are icy bodies. Most of them are small, no more than a few miles across. Some may be larger. Some may be the size of dwarf planets. What they are made of is mostly water ice, with significant amounts of carbon dioxide ice, methane ice, ammonia ice, and various complex organic compounds. Many of them are essentially preserved samples of the original solar nebula, the cloud of gas and dust from which the Sun and planets formed 4.5 billion years ago. They have been frozen in deep cold ever since. The temperature in the Oort Cloud is barely above absolute zero, around minus 440 degrees Fahrenheit. At that temperature, chemistry stops. Most physical processes slow down. The objects do not change. They do not age in any meaningful sense. They have been sitting in the dark, in the cold, for 4.5 billion years, in essentially the same state they took when they first condensed out of the early solar system. Some of them carry organic chemistry that may date back even further than that. Comets, when they pass through the inner solar system, and we can examine them, often contain amino acids and other prebiotic molecules. These are the kinds of chemicals that, on Earth, eventually became the building blocks of life. The Oort Cloud is, in this sense, a vast freezer full of preserved samples of the early universe's chemistry. Each comet is a small museum exhibit. The density of objects in the cloud is, by our standards, vanishingly low. Even though there are trillions of comets in the cloud, the volume of space the cloud occupies is so enormous that the comets are extraordinarily spread out. The average distance between one comet and the next in the main body of the Oort Cloud is something like a few 100 million miles. That is more than the distance from the Earth to Mars at their closest approach. If you teleported to a random point in the Oort Cloud, you would, in most cases, see nothing around you. No comets visible to the naked eye, no nearby objects of any kind. You would be in a perfectly empty volume of space, dark beyond imagining, illuminated only faintly by a sun that was now just another star. The nearest comet might be 100 million miles away, or further, drifting silently, alone. The Oort Cloud is not a dense shell, like the shell of an egg. It is more like an extremely diluted mist. The cloud is real. Its objects are real. But to be inside, it is, in most places, to be inside something that feels exactly like emptiness. If you tried to take an inventory of what is in the Oort Cloud, the numbers are difficult to communicate. There are perhaps 1 trillion to 2 trillion objects larger than about half a mile across. If you include smaller objects, the population is much larger. Some estimates suggest there may be 10 trillion or more small icy bodies in the cloud, ranging from the size of small mountains down to the size of houses or cars or pebbles. The exact total is impossible to determine, because we can only see the largest ones and only when they fall inward toward the sun. The mass of the cloud, however, is surprisingly small. Despite containing trillions of objects, the total mass is estimated to be only a few times the mass of Earth, possibly as much as 10 Earth masses, possibly less. The cloud is mostly empty space, populated by relatively small bodies spread across an enormous volume. The bulk of the matter in the solar system is in the sun. The bulk of the rest is in the planets. The Oort Cloud, by mass, is a small contribution. By number of objects, it dominates. Think about that for a moment. The largest structure in the solar system contains a relatively small amount of matter. Most of the volume it occupies is just empty space. The cloud is not a dense ring or a packed sphere. It is a vast, thin haze, with individual objects scattered through it at enormous separations. This is why we cannot easily detect it. The objects are too dispersed. Even with our best telescopes, we can only see the rare ones that come close enough to be illuminated by the sun. The vast majority remain in the dark, invisible, undetected, drifting on their long, slow orbits through volumes of space that no other matter inhabits. There is a way to get a feeling for the scale of all this, and it involves the fastest object humanity has ever launched into deep space. The Voyager 1 spacecraft launched in 1977. It is now traveling at approximately 38,000 miles per hour, which is roughly 17 kilometers per second. It has been moving at that speed for almost 50 years. Nothing humans have ever built is traveling faster than Voyager 1 in any direction away from the sun. Voyager 1 is now roughly 15 billion miles from Earth. It has crossed the heliopause, the boundary where the sun's solar wind ends. It is, technically, in interstellar space, by the loose definition that the term implies. It is no longer inside the sun's protective bubble of charged particles. But Voyager 1 has not reached the Oort Cloud, not the outer edge, not the main body, not even the inner edge. Voyager 1 will reach the inner edge of the Oort Cloud, the inner Oort Cloud, or Hills Cloud, in approximately 300 more years. By the year 2320 or so, long after every engineer who built it has died, long after every scientist who studies it today has died, long after most of the cities that fund the mission have grown and changed beyond recognition. That is the inner edge. To pass through the entire Oort Cloud, to reach the outer boundary where the sun's territory finally yields to the broader galaxy, Voyager 1 will take approximately 30,000 years. 30,000 years. The entire history of human civilization, from the first cities to today, is about 12,000 years. Voyager 1 will spend more than twice the entire span of human civilization just crossing the Oort Cloud, and it will be moving fast the whole time. Faster than any human-made object has ever moved through deep space. 38,000 miles per hour for 30,000 years. The distance it will cover in that span is so great that the human brain cannot really hold it. By the time Voyager 1 finally crosses the outer edge of the Oort Cloud, the spacecraft itself will be unrecognizable. Its instruments will have been dead for tens of thousands of years. Its radio will have been silent for nearly as long. Its components will have been slowly degraded by cosmic rays and the slow passage of time. It will be a piece of debris drifting outward, no longer functioning as a spacecraft in any meaningful sense. But it will still be moving, and it will eventually leave our solar system entirely. The Oort Cloud is not a destination. It is a journey that none of us will live to see completed. There is something quietly humbling about that. Voyager 1 is the proudest engineering achievement of our species, in some ways. It is the furthest reach of our technology, the longest-lived mission in space history, the fastest sustained object we have ever sent outward. And it is still, after 50 years of travel, less than 2% of the way to the outer edge of just the inner Oort Cloud. The Oort Cloud is so large that it makes our most ambitious works of engineering look like children's toys. To put this in perspective, consider what 30,000 years actually means. 30,000 years ago, the last ice age was still in its final stages. Mammoths still walked the earth. Humans had not yet domesticated animals. They were still hunter-gatherers, painting on cave walls, telling stories around fires, looking up at a sky that was nearly identical to the one we see today, because the stars have barely moved in 30,000 years. Now imagine all of that history happening one more time, from now into the future, from this moment, 30,000 years forward. Every civilization rising and falling, every language born and forgotten, every individual human life, every city built and abandoned, every war fought, every peace made, all of it happening one more time. That is roughly how long Voyager 1 will take to cross the Oort Cloud. And it is moving at 38,000 miles per hour the entire way. If a different civilization, on a different planet around a different star, looked at our sun and watched Voyager 1's slow crossing of the Oort Cloud, they would see almost no motion at all. Even over centuries of patient observation, Voyager would barely shift. The cloud is so large, and the relative speeds are so small in galactic terms, that the spacecraft's progress through it would be imperceptible from any reasonable distance. This is the architecture of the place where we live. We have planets, and we know them well, and we have rings of small bodies that we know less well, and beyond all of that, we have this, a structure that holds trillions of objects, that surrounds everything we have ever explored, that bleeds outward toward the nearest stars, and that we have built our entire picture of from inference, from gravity, from the rare comets that have fallen all the way inward to where we could see them. It is the largest single feature of our home. The Oort Cloud is not static. It looks, when described in textbooks, like a fixed structure, a permanent shell of icy bodies surrounding the sun. But that picture is wrong, in subtle ways. The cloud is moving, its objects are slowly drifting, and forces from outside the solar system are constantly working on it, sometimes pushing objects loose, sometimes pulling them inward, sometimes ejecting them entirely. The first of these forces is something called the galactic tide. The Milky Way is a vast disk of stars, with the Sun and the solar system located roughly halfway out from the center. The whole disk rotates, slowly, with the Sun orbiting the galactic center once every 230 million years. The galaxy is not a uniform structure. There is more mass toward the center. There is less mass at the outer edges. There is a dense, thin layer of stars within the plane of the disk, and a more diffuse halo of stars above and below it. All of these mass distributions exert gravitational pulls. Most of them are too weak to affect anything within the inner solar system. The Sun's gravity, close in, is much stronger than the gravity from any of these other sources. But out at the Oort Cloud, the Sun's gravity has weakened so much that the gravitational pulls from the rest of the galaxy become significant. Specifically, the differential pull of the galactic disk, which is denser in the plane than perpendicular to it, exerts a slow tidal force on the outer regions of the solar system. It is similar in concept to the way the moon raises tides on Earth's oceans, though the mechanism is different. The galactic tide pulls on the Oort Cloud differently depending on which direction an object is from the Sun. Objects directly above or below the galactic plane feel a slightly different pull than objects to the side. Over millions of years, this slow tide warps the Oort cloud. It nudges objects. Some are pushed inward, some are pushed outward. The orbits of the cloud's objects are constantly being adjusted, very slowly, by the gravitational structure of the galaxy itself. The galaxy is stirring our own backyard, imperceptibly, slowly, constantly. The Oort cloud we have today is not the same Oort cloud that existed 1 billion years ago. Many of the objects that were in the cloud 1 billion years ago have been ejected, either inward toward the sun or outward into interstellar space. Many objects that are in the cloud today were not there 1 billion years ago, having been captured from elsewhere or having had their orbits shifted into the cloud. The cloud is a slowly churning population. It looks static on human timescales. On galactic timescales, it is in constant motion. There is a second force that disturbs the Oort cloud, and it is more dramatic than the galactic tide. Stars move. The galaxy is full of them, and they all orbit the galactic center on their own paths. Most of them are far away from the sun, and they stay far away. But occasionally, on the slow timescales of galactic motion, one comes close. Astronomers have calculated that, on average, a star passes within 1 light year of the sun roughly every 100,000 years. Within half a light year, every few 100,000 years. Within 1/10 of a light year, every 10 million years or so. And on rare occasions, every few 100 million years, a star may pass within a few thousand astronomical units of the sun, close enough to enter the outer reaches of our Oort cloud. When this happens, the gravitational disturbance is significant. The passing star, even though it is far enough away to be invisible to anyone in the inner solar system, exerts a strong enough pull on objects in the outer Oort cloud to substantially alter their orbits. Some objects are flung outward, ejected from the solar system entirely. Some are pulled into the passing star's gravitational influence and captured. Some are knocked inward, sent on long, slow journeys toward the inner solar system, where they will eventually appear as comets. We can identify, with some confidence, several stars that have come close to the sun in the past. The most famous example is a small red dwarf star called Schultz's star, named after the astronomer who discovered it. Schultz's star passed within about half a light year of the sun roughly 70,000 years ago. It came close enough that it almost certainly disturbed the Oort cloud. Some of the comets we see today, especially long-period comets falling inward from the outer reaches of the cloud, may have been knocked loose by Schultz's star during its passage. The thought is strange when you consider it carefully. There are people alive today whose distant ancestors, 60 or 70,000 years ago, might have looked up at the sky and seen Schultz's star as a faint reddish point of light. It would have been visible to the naked eye, just barely, for a few thousand years. Then it would have moved on. The same stars they saw have continued to move. Some of the stars in the sky today have passed close to the sun in the past. Some will pass close in the future. There is a star called Gliese 710, currently about 63 light-years away. It is moving toward us. In about 1.3 million years, it will pass within roughly 1 light-year of the sun. That is close enough to disturb the Oort cloud substantially. After that pass, we may see an increase in long-period comets arriving in the inner solar system, possibly for thousands of years afterward. We cannot predict exactly what will happen. The dynamics are too complex. We can only know that Gliese 710 will pass, that it will disturb the cloud, and that some objects, somewhere in the cloud, will be set loose. Stars we can see in the night sky today have passed through our Oort cloud before. Stars that don't exist yet will pass through it in the future. The galaxy is alive with motion, and the Oort Cloud is one of the structures that feels every passing star, every distant gravitational tug, every slow shift in the configuration of the local universe. There is a more dramatic and more controversial idea about what disturbs the Oort Cloud. In 1984, two pairs of astronomers working independently proposed that the Sun might have a companion star, not a star bright enough to see easily, or close enough to obviously affect the planets. Something dimmer, something further out. A red dwarf perhaps, or a brown dwarf in a highly elongated orbit around the Sun, taking roughly 26 million years to complete a single circuit. They called it Nemesis. The motivation for the hypothesis came from a different field entirely. Paleontologists had noticed, in the fossil record, that mass extinction events on Earth seem to occur roughly every 26 million years. Not every extinction, not all of them, but the big ones, the major die-offs, the events where significant fractions of all species disappeared in a relatively short period. There was a statistical signal, faint but present, suggesting a roughly 26 million year cycle of catastrophic events. What could possibly cause such a regular cycle? Earth itself does not have any obvious geological process that would produce extinction events on that timescale. Volcanic activity, plate tectonics, climate cycles, none of these have a 26 million year period. Something outside the Earth was needed, something cosmic. The Nemesis hypothesis proposed that the Sun has a dim companion currently far away that approaches the Sun every 26 million years. As Nemesis swings past, it disturbs the Oort Cloud, sending a shower of comets inward. Some of those comets eventually strike Earth. The largest of them cause mass extinctions. It is a beautiful hypothesis. It connects two seemingly unrelated patterns, the periodicity of extinctions and the architecture of the outer solar system, into a single explanation. It is also almost certainly wrong. Decades of searching with infrared telescopes have failed to find Nemesis. By the early 2010s, multiple all-sky infrared surveys had ruled out any companion star to the Sun within several light years. There is no Nemesis. There is no dim red dwarf or brown dwarf in a long orbit around the Sun. If such an object existed, we would have found it by now. The statistical signal in the extinction record, when re-examined with more careful methods, has also weakened. Some studies still find a faint periodicity. Others find none. The original claim of a 26 million year cycle is now considered, at best, suggestive, and possibly an artifact of the way the data was originally analyzed. So the Nemesis hypothesis is, for the moment, in the speculative graveyard. It is not impossible that some periodic mechanism exists, perhaps related to the Sun's motion through the galactic disk, or to encounters with dense regions of interstellar material. But Nemesis itself, the dim companion star, is not real. We are confident enough of that to put it aside. And yet, the idea is hard to fully release. There is something compelling about the picture. A dark twin to our Sun, hidden in the deep cold of the outer solar system, swinging close every 26 million years to send showers of ice toward our small blue planet. Each pass, a wave of destruction. Each pass, a renewal of the cycle. It is the kind of cosmic horror that good science fiction is built from. The fact that it is probably not true does not stop it from being a useful way to think about the kinds of disturbances that can, and do, affect the Oort Cloud. The hypothesis also reminds us of something important about astronomy. The history of the field is full of objects that turned out to be real, even though they were proposed for theoretical reasons before they were observed. Neptune was predicted on the basis of irregularities in the orbit of Uranus. The neutrino was proposed by Wolfgang Pauli to explain energy conservation in beta decay, decades before it was actually detected. The cosmic microwave background was predicted by Ralph Alpha and Robert Herman in 1948, almost 2 decades before Penzias and Wilson stumbled upon it. Many features of the universe were inferred from indirect evidence long before they were directly observed. So when astronomers proposed nemesis, they were doing something that the field had often done before. They were saying, here is a pattern in the data. Here is a hypothesis that would explain it. Let us go look. They went and looked. They did not find it. That is how science is supposed to work. The hypothesis is now mostly retired, not because it was unreasonable, but because the searches that should have found it did not. Nature, in this case, said no. The cloud is, in some sense, an armory. Things shake it. Some of them have shaken it in the past. Some of them will shake it in the future. We do not always know which or when. The nemesis hypothesis was the most dramatic version of this idea, and even if nemesis itself does not exist, the basic concept remains. Something disturbs the cloud, occasionally. Things fall. Most of what falls from the Oort Cloud, when it falls, becomes a comet. We see it. We name it. We track it. We watch it cross the sky for weeks or months, growing brighter as it approaches the sun, developing its long tail of vaporized ice and dust, and then receding back into the dark. The famous comets are mostly Oort Cloud comets. Hale-Bopp, which crossed the sky in 1997 and was visible to the naked eye for 18 months, the longest of any comet in modern history. People who were alive then remember it. It hung in the western sky after sunset, brighter than most of the stars, its tail stretching upward like a streak of pale paint across the heavens. Hyakutake, which passed close to Earth in 1996, displaying a tail that stretched across a quarter of the sky. The Great Comet of 1811, which was visible for 9 months and inspired writers and artists across Europe. Tolstoy wrote about it. Napoleon's army marched into Russia under its light. Each of these came from the Oort Cloud, fell inward over thousands or millions of years, and gave us a few months of light before continuing on or being broken apart. Hale-Bopp will not return for about 2,400 years. The next time it crosses the sky, the people watching it, if there are any, will not share a language with us. They may not share a civilization with us. The empires of the year 4400 will be as foreign to us as the empires of 70,000 years ago. And yet, the comet will return, on schedule, swinging back from the deep cold to greet whoever is here to greet it. Hyakutake will not return for about 70,000 years. There is no continuity of human civilization that will see Hyakutake again. Whoever sees it next will have inherited the Earth from us across an unimaginable span of generations. The comet does not care. It will arrive regardless, on its own slow schedule, and put on its show, and leave again. These are the slow visitors, the patient ones. They come from very far away, they show themselves briefly, and they return to where they came from, on timescales that have nothing to do with us. It is worth pausing to consider what it means to share the sky with these objects, even briefly. When Hale-Bopp hung in the western sky in 1997, it was visible to nearly every human being on Earth who lived in a place dark enough to see the stars. Billions of people looking up at the same point of light, knowing, on some level, that they were watching something old, something that had been traveling for thousands of years before any of them were born, something that would continue to travel for thousands more years after they were dead. The comet did not know any of them were looking. The comet did not care. It was simply on its orbit, doing what it had been doing for the entire length of its existence. Comets have, throughout history, been one of the few things that briefly unite human attention across cultures and continents. Wars stop sometimes when comets appear. People who otherwise would never have looked at the sky look up. Old questions get asked again. Children ask their parents what it is. Parents try to explain. The comet, indifferent to all of this, continues across the sky and then, eventually, vanishes back into the dark from which it came. The comets we see are tiny ambassadors of a place no human will ever visit. They are, in a real sense, the only direct contact we have with the Oort Cloud. Everything else is inference, mathematics, theory. The comets themselves are the cloud's only physical messengers. The only objects from that vast invisible structure that we ever get to touch, photograph, study, or examine. And each one, when it comes, is a single visit, a single chance to learn something. We will not see it again. But not every Oort Cloud object that falls inward becomes a quiet comet that crosses the sky and leaves no trace. Some of them strike things. The largest impact event in Earth's recent geological history was the Chicxulub impact, 66 million years ago. An object, roughly 6 to 9 miles across, struck the Yucatan Peninsula in what is now Mexico. The impact released energy equivalent to billions of nuclear weapons. It triggered global wildfires, threw enough dust into the atmosphere to darken the sky for years, dropped global temperatures by tens of degrees, and ended the reign of the non-avian dinosaurs, along with roughly 3/4 of all species on Earth at the time. What was the Chicxulub impactor? Where did it come from? This is, surprisingly, still debated. For decades, the leading hypothesis was that it was an asteroid from the main asteroid belt between Mars and Jupiter. Specifically, it was thought to be a fragment of a larger asteroid that had been broken up by a collision in the belt, sending pieces inward toward the inner solar system. Some of those pieces eventually crossed Earth's orbit, and one of them, the Chicxulub impactor, found its target. In recent years, some researchers have proposed an alternative. They have argued, based on the impactor's chemistry and trajectory, that it may have been a comet, not an asteroid, specifically an Oort Cloud comet, a long-period object knocked inward from the deep cold of the outer solar system that happened to cross Earth's path. The evidence is not conclusive. The asteroid hypothesis is still the leading one. Most planetary scientists still believe the Chicxulub impactor was an asteroid. But the comet hypothesis is not crazy. It is plausible enough to be taken seriously. And the question of where the dinosaur killer came from is still genuinely open. Either way, the dynamics of how things reach Earth from the outer solar system are the same. Some object, somewhere, is disturbed. The disturbance might come from the galactic tide, or from a passing star, or from gravitational interactions with other objects, or from forces we have not yet identified. The object falls inward. It takes a very long time to fall, sometimes millions of years. At some point, it crosses the orbit of Earth. Most of these encounters are near misses. Most objects that cross Earth's orbit do so without hitting us. The Earth is small, the solar system is enormous, and the probability of any single object hitting any single small target is vanishingly low. But over the course of billions of years, even vanishingly low probabilities add up. The Earth has been hit before. It will be hit again. Most of these impacts will be small, harmless, the kind that produce a meteor in the upper atmosphere and nothing more. Some will be larger. The geological record shows scattered across hundreds of millions of years, the marks of impacts that did real damage. We do not know with any confidence how many of those impacts originated in the Oort Cloud. The fossil record and the geological record cannot tell us in most cases what the impactor was made of or where it came from. We can identify some impactors as asteroids, by their chemistry, some as cometary, by indirect evidence. Most we simply do not know. The Oort Cloud is not a constant threat. The probability of any individual Oort Cloud object hitting Earth in any given year is extremely small. We are far more likely to be hit by an asteroid from the much closer asteroid belt. Earth's monitoring systems are increasingly capable of identifying objects on potential collision courses with us, years or decades in advance. But the Oort Cloud is part of the story. Things do fall sometimes from very far away. The cloud is one of the places they come from. There is no need to panic about this. The cloud is not actively shaking us with regularity. The Nemesis hypothesis was wrong. There is no 26 million year cycle of imminent doom. The processes are slow. The probabilities are low. And the inner solar system is mostly stable across human timescales. But the cloud is real. The objects are real. The forces that disturb the cloud are real. And occasionally, on geological timescales, things from the cloud reach us. Sometimes they cross our sky as quiet visitors, beautiful and harmless. Sometimes, much less often, they do not. For every comet that reaches the inner solar system, trillions remain in the dark, undisturbed for billions of years. The cloud is mostly silent, mostly still. The visitors are the rare exception. But the visitors are why we know the cloud is there at all. We are going to slow down now. We have walked outward through the planets, through the Kuiper Belt, through the heliopause, through the inner Oort Cloud, through the outer Oort Cloud, all the way to the place where the sun's gravity finally weakens to nothing. We have looked at what disturbs the cloud, what falls from it, and what those falls can sometimes do. Now, we are going to sit with the structure for a while. Not measure it, not catalogue it, just sit with it. Because the Oort Cloud is not just a feature of our solar system. It is also a way of thinking about what it means to belong to a star and what the boundary of belonging actually looks like. Here is the simple question that turns out to be hard. Where does the solar system end? Most people, if you ask them, will say something like, at Neptune's orbit, or at Pluto, or at the edge of the Kuiper Belt. These are the natural answers. They reflect what you see when you look at a simplified diagram of the solar system. The planets are arranged in concentric circles. Beyond them is empty space. The solar system, in this picture, has a clear and definite boundary. But the question is harder than that. Where does the solar system end? If you mean, where do the planets end? Then the answer is Neptune, at 30 astronomical units. That is the orbit of the outermost major planet. If you mean, where does the disk of small bodies that orbits in the same plane as the planets end? Then the answer is the outer edge of the Kuiper Belt at roughly 50 astronomical units. If you mean, where does the sun's solar wind end? Where the bubble of charged particles that the sun blows out into space gives way to the broader gas of the interstellar medium? Then the answer is the heliopause, at roughly 120 astronomical units. This is where Voyager 1 crossed in 2012. It is where the sun's influence, in one sense, ends. But if you mean, where does the sun's gravitational influence end? Where the territory of objects bound to our star gives way to the territory of objects bound to other stars, then the answer is the outer edge of the Oort Cloud. At 100,000 astronomical units, give or take, possibly further. There is no single edge. There are several different edges, depending on what definition you use. And the edge that matters most, in some ways, is the gravitational one, because that is the edge of where our sun has any meaningful pull. That is the edge of what the sun owns. And here is the strange thing. The Oort cloud does not end with a wall. It thins, gradually. Its objects become sparser, and sparser, and sparser. The further out you go, there is no sharp boundary. There is no point at which you can say, here, this is the edge, beyond which lies something else. The cloud just fades, slowly, into the broader emptiness of interstellar space. And the gravitational pull of the sun fades with it. At 100,000 astronomical units, the sun's gravity is no longer the dominant force on any object. The galactic tide is comparable. The gravitational pull of the nearest stars is comparable. The pull of more distant masses summed up is comparable. One system fades into another. There is no instant of transition. There is no border to cross. We are not surrounded by emptiness. We are surrounded by a gradient, an almost imperceptible transition from ours to theirs, and there is no line. This is, when you think about it carefully, a strange way for a solar system to be organized. We are taught, as children, that the solar system is a distinct thing, the sun and its planets, separate from everything else. But the reality is that the solar system shades slowly into the rest of the galaxy. Where one system ends and another begins is a matter of definition, not a matter of geometry. We belong to the sun. But we belong to the sun progressively less the further out you go. At Pluto, we are fully within the sun's gravitational territory. At the inner Oort cloud, mostly. At the outer Oort cloud, barely. Beyond that, we belong to no one in particular, but to the gravitational sum of everything in the galaxy. This is, perhaps, a more accurate way to think about belonging in general. Most things in the universe do not have sharp edges. They have gradients. They fade into other things. The lines we draw between systems, between objects, between regions, are usually conveniences for our own thinking, not features of the underlying reality. The reality is mostly gradient, mostly transition, mostly slow shading from one thing into another. We come from the sun. The sun made us, in a sense. The material in our bodies, the chemistry that lets us think and breathe and move, was forged in older stars and then collected slowly into the cloud that became our solar system. We are, in this sense, a product of the sun and what came before it. We belong to the sun's history, but the sun's history shades into the history of the galaxy. The cloud the sun formed from was itself made of material that came from elsewhere. The material in the Oort cloud is, in part, captured from other systems. The boundaries are porous. The categories overlap. The sun is one node in a vast network of stars, all of them connected by slow exchanges of matter, all of them sharing some material with their neighbors, all of them contributing to and drawing from the broader chemistry of the galaxy. We are children of the sun. We are also children of the galaxy. The two are not separate. And the Oort cloud is where, more than anywhere else, the boundary between the two becomes hard to find. If the Oort cloud fades gradually, and other stars have their own Oort clouds, then it is possible, in principle, for them to overlap. This is not just a theoretical possibility. It is the most likely state of affairs. Every star, when it forms, goes through roughly the same process. It condenses out of a cloud of gas and dust. It builds a disk of debris around itself, from which planets form. The chaotic gravitational dynamics of planet formation in the early stages fling many small bodies outward into the outer reaches of the new system. These outward flung bodies, over millions of years, settle into long, loose orbits that eventually constitute the system's own Oort Cloud. This is how our Oort Cloud formed. It is how, almost certainly, the Oort clouds of other stars form. Most planetary systems are likely to have them. The nearest star system to our own is Alpha Centauri at about 4.3 light-years. Alpha Centauri is actually a triple system, 3 stars, 2 of them sun-like, and 1 a small red dwarf called Proxima Centauri. The 2 sun-like stars almost certainly have planets. Proxima Centauri certainly does, including at least 1 rocky planet in its habitable zone. Alpha Centauri, then, almost certainly has its own Oort cloud or set of Oort clouds surrounding it. The outer edge of that cloud may extend out to 100,000 astronomical units or more from the system, just like ours. Now here is the thing. Alpha Centauri is about 270,000 astronomical units from the Sun. Half that distance is 135,000 astronomical units. If our Oort cloud extends out to 100,000 astronomical units, and Alpha Centauri's Oort cloud extends out to 100,000 astronomical units, then the outer reaches of the 2 clouds may meet somewhere in the middle. Our Oort cloud and the Oort cloud of Alpha Centauri may already be touching. The outer shells of our 2 solar systems may be intermingled. Some of the objects that orbit in our Oort cloud on the side facing Alpha Centauri may, at certain points in their orbits, be closer to Alpha Centauri than to us. They may be in a kind of gravitational borderland where the pull of the Sun is no longer clearly stronger than the pull of the other system. Over billions of years, these borderland objects may switch teams. Some objects that started in our Oort cloud may end up bound, instead, to Alpha Centauri. Some objects that started in Alpha Centauri's cloud may end up bound to us. The exchange is slow, and the numbers involved are unclear, but the process is real. Material has been moving between solar systems very slowly for the entire history of the galaxy. This is a strange thought. The solar system is not a closed, sealed thing. It is, at its outer edges, porous. It exchanges material with its neighbors. Some of what is ours, somewhere out there, originally came from somewhere else. Some of what is theirs, somewhere out there, originally came from us. The exchange has been confirmed, recently, by direct observation. In 2017, an unusual object passed through the inner solar system. It was first noticed by the Pan-STARRS telescope on Mount Haleakala in Hawaii on the 19th of October, 2017. It was small, only a few hundred feet long. It was moving extremely fast, fast enough that its trajectory was clearly hyperbolic. It was not bound to the Sun. It was not part of our solar system. It had come from somewhere else, was passing through, and would leave again, never to return. It was named Oumuamua, a Hawaiian word meaning, roughly, scout or first messenger from afar. Oumuamua was the first confirmed interstellar object ever to pass through our solar system. The first thing we had ever directly observed coming in from outside. There had been theoretical predictions for decades that such objects must exist, that small bodies must occasionally drift between solar systems. But we had never seen one. Until that October, in 2017, when one passed close enough to detect, Oumuamua was strange. It was shaped unusually, possibly elongated, possibly cigar-shaped, possibly more like a flat disk, though the exact shape was difficult to determine. Its brightness varied dramatically as it rotated, suggesting it had extreme proportions, perhaps 10 times longer than it was wide. No object in our own solar system has shape like that. It was tumbling, end over end, completing one rotation every 8 hours or so, in a way that suggested it had been knocked into that motion long ago and had never stabilized. It also accelerated slightly as it left the solar system, in a way that was not entirely explained by gravity alone. The acceleration was small but measurable. Some researchers proposed that it was outgassing, like a comet, but its outgassing was unusual, with no visible tail and no detectable jets of gas. A few researchers, including the prominent Harvard astronomer Avi Loeb, proposed more exotic explanations, including the possibility that Oumuamua was an artificial object, a piece of alien technology, perhaps a light sail, or a derelict probe. This remains a minority view. The most accepted explanation is that Oumuamua was an unusual kind of interstellar comet, perhaps made of pure hydrogen ice or some other material that outgassed without leaving visible traces. The truth is, we do not fully know. Oumuamua passed through too quickly. Our telescopes could only track it for a few weeks before it became too faint to observe. By the time anyone could organize a serious follow-up study, it was already gone, accelerating outward on its hyperbolic trajectory, never to return. The data we collected during those few weeks is all the data we will ever have. The mystery will not be solved by going back to look. We can only argue indefinitely about what we saw. Whatever Oumuamua was, it had come from another solar system. It had been traveling through interstellar space for possibly hundreds of millions of years. It had passed through the outer reaches of our solar system, swung close to the sun, and then continued on its way. It will not return. It is now leaving the solar system, never to be seen again by us, heading toward another star, somewhere, billions of years from now. 2 years later, in 2019, an amateur astronomer in Crimea named Gennady Borisov discovered a second interstellar object. This one was unmistakably a comet, with a visible tail and active outgassing. It was named Borisov after its discoverer. Its trajectory was clearly hyperbolic, like Oumuamua's. It had come from another star system. It was passing through. What was striking about Borisov was how ordinary it looked. Despite coming from somewhere else, despite being a foreign object in our solar system, Borisov's chemistry was almost identical to that of our own comets. The same water ice, the same carbon dioxide, the same cyanogen and other organic molecules. A comet from another star entered our solar system. It looked like it came from home. We watched it pass. We could not reach it. It continued on its way. We had several months to study Borisov as it passed through. Spectroscopic analysis of its tail revealed water, carbon monoxide, hydrogen cyanide, and the same family of organic molecules we find in our own comets. The ratios were slightly different than typical solar system comets, but only slightly. If you handed an astronomer the chemistry data from Borisov, without telling them where the object came from, they might not be able to identify it as an interstellar visitor. It looked, by every reasonable measure, like one of ours. This is, when you think about it carefully, a strange piece of news. We had assumed for centuries that the chemistry of our solar system was distinctive, that our particular history, our particular star, our particular sequence of events would have produced a particular kind of cosmic chemistry that was, in some sense, ours. The discovery of Borisov suggested otherwise. The chemistry of comets, the slow chemistry of the outer regions of planetary systems, is, apparently, mostly the same wherever in the galaxy you look. The implication is striking. Comets, it seems, are mostly the same wherever they come from. The chemistry of the outer regions of planetary systems is, apparently, quite similar across the galaxy. The Oort clouds of different stars contain objects that, when you look at them up close, are almost indistinguishable from our own. Since Borisov, more interstellar objects have been detected. The numbers are still small, but they are growing. The Vera C, Rubin Observatory, which began full operations in 2025, is expected to detect many more. It is designed to scan the entire visible sky every few nights, looking for moving objects. Many of those objects, almost certainly, will turn out to be interstellar visitors from other stars. Over the coming decades, our catalogue of interstellar objects will grow. We will start to see the patterns. We will start to understand the population. We will learn things about how solar systems exchange material slowly across the galaxy. We are not unique in this. The cloud around our sun is one of many. The clouds around other stars are real, and they look very much like ours, and occasionally, on rare occasions, they send us a visitor we can observe. If we accept that almost every star likely has its own Oort cloud, then we are forced to revise our picture of what the galaxy actually is. We tend to think of the Milky Way as being made of stars. 200 billion of them, give or take, arranged in a spiral disk with a central bulge and a surrounding halo. Between the stars, we picture, is mostly empty space. Some interstellar gas, some dust, the occasional nebula, but mostly nothing. This picture is, in a quantitative sense, wrong. The stars are real. They are bright. They are visible. They are where almost all of the galaxy's mass and luminosity is concentrated, but by volume, by sheer cubic volume of space, the stars are vanishingly small compared to everything else in the galaxy. Most of the volume of the galaxy is occupied not by stars, but by the spaces between them. And those spaces are not empty. Around each star, on average, there is an Oort cloud, or something like it, extending out to tens or hundreds of thousands of astronomical units. The clouds of nearby stars may overlap or come very close to overlapping. The clouds themselves contain trillions of icy bodies each. So the galaxy, at this scale, is not mostly stars. It is not mostly empty space. It is mostly this, the cold, dark, invisible architecture of comet clouds surrounding every star, filling almost every cubic light year of the galactic disk. There are, in the Milky Way, somewhere on the order of 100 billion times a trillion icy bodies. 100 sextillion, that is, a 1 followed by 23 zeros. More icy comet-sized bodies than there are stars by many orders of magnitude. More than there are grains of sand on every beach on Earth, multiplied by every grain of sand in every desert. The galaxy is full. It is not the sparse, mostly empty thing we picture. It is, mostly, this slow, dark, frozen architecture that surrounds every star, fills the space between every system, and constitutes the bulk of the matter in the disk. We do not see it. We cannot see it. It is invisible to any telescope we have ever built, except in the rarest cases where one of its objects falls inward toward a star and warms up enough to emit light. But it is there. It is the dominant component of the galaxy by number, if not by mass. And our sun's cloud is only one of 200 billion. Comets carry organic chemistry. This has been confirmed many times. When a comet from the Oort cloud falls inward and we can examine it, either with telescopes or, in a few cases, with spacecraft, we find a rich brew of organic molecules, amino acids, the building blocks of proteins. Glycine, the simplest amino acid, has been detected in multiple comets. Other amino acids, more complex ones, have been found in trace amounts. Sugars have been detected. Nucleobases, the components of DNA and RNA, have been detected in some samples. This is striking, because amino acids and other prebiotic molecules are the kinds of chemistry that, on Earth, eventually led to the emergence of life. The transition from prebiotic chemistry to biology is one of the deepest mysteries in science. We do not understand exactly how it happened here on Earth between 4 and 3.5 billion years ago. But we know it involved chemistry roughly like what we find in comets. This raises a question that has been around for more than a century. Could life, or the chemistry of life, have come to Earth from somewhere else? Could comets, falling from the Oort Cloud, have delivered the building blocks of biology to the early Earth? Could those building blocks have been the seeds from which everything we know about life eventually grew? This is called the panspermia hypothesis. It comes in various flavors, some more scientifically respectable than others. The weakest form simply says that the organic chemistry we find in comets is similar to the organic chemistry that eventually became life on Earth, and that comets may have delivered significant amounts of that chemistry to the early Earth during the heavy bombardment, helping to seed the prebiotic chemistry from which life eventually emerged. This version is widely accepted as plausible, and probably even likely. A stronger version says that life itself, in its earliest forms, may have traveled between solar systems on objects like comets. Bacterial spores embedded in ice, drifting between stars for millions of years, eventually delivered to warm worlds where they could thrive. This version is more speculative. The challenges of survival in interstellar space over geological timescales are significant. Most biologists are skeptical, though not all dismiss it. The strongest versions of panspermia are basically untestable and not widely accepted. They propose that life is being actively spread between solar systems by some intentional process, or that all life in the galaxy descends from a common origin. These are interesting to think about, but the evidence is essentially non-existent. What is interesting is the weaker form, the form that says the chemistry of the Oort Cloud and of the clouds of other stars is the same chemistry that became life on Earth. The cloud is full of the molecules that biology is made of, and these molecules occasionally fall. The numbers, when you start running them, are surprisingly large. During the period known as the Late Heavy Bombardment, between about 4.1 and 3.8 billion years ago, the Earth was hit by an enormous number of comets and asteroids. Some of those, almost certainly, came from the Oort Cloud. Together, they may have delivered to the early Earth a significant fraction of all the water and organic chemistry that we have today. The oceans, by some calculations, were filled, at least in part, by ice that fell from the deep cold of the outer solar system. If true, this means something quietly remarkable. The water you are drinking right now may have spent billions of years frozen in a comet, drifting in the outer reaches of the Oort Cloud, before being knocked inward by some gravitational disturbance, falling through space for millions of years, and finally arriving on the surface of the early Earth. The molecules that make up your body may have been part of the chemistry of the cloud before they were part of you. This is true in some sense, regardless of whether the stronger forms of panspermia turn out to be correct. The chemistry of life is the chemistry of the universe. The atoms in your body, the carbon, the oxygen, the hydrogen, the nitrogen, came originally from stars that died long before our sun was born. Their material became part of the cloud from which our sun formed. Some of that material is now in your body. Some is still in the Oort Cloud, waiting. We cannot answer the deeper question, the one about whether the chemistry of life is being spread between solar systems. But we can ask it, and the fact that we can ask it, and that we have some evidence to consider, means the Oort cloud is not just a boundary. It is a possible bridge. Let us pull back now from the chemistry and the gravity and just sit with what we have established. The Oort cloud surrounds our entire solar system. It contains trillions of objects. It extends from beyond the Kuiper belt all the way to nearly halfway to the nearest star. It is the largest structure in our home. It defines, in the most fundamental gravitational sense, where our system ends. We have never seen it. Nobody on Earth ever has taken a photograph of the Oort cloud. We have not visited it. We have not measured it directly. We have no instruments capable of detecting it, except by catching the rare visitor that falls all the way inward to where we can see it. Everything we know about the Oort cloud, we know by inference. From mathematics, from the trajectories of long-period comets, from models of how solar systems form, from observations of other stars and their dust disks, from rare interstellar visitors like Oumuamua and Borisov. Piece by piece, over centuries, we have built up a picture of a structure that by every direct measure we should not be able to know exists. And yet, we are certain. The Oort cloud is real. It is around us. It always has been. Every human being who has ever lived has spent their entire life inside the cloud without knowing it. The cloud is older than our species by billions of years. It will outlast our species by billions of years. It is the silent, invisible context in which everything we have ever done has happened. When you walk outside tonight and look up at the stars, you are looking at points of light that have traveled through the outer reaches of our Oort cloud to reach you. The light you see has passed through or around trillions of frozen, icy bodies, none of which were bright enough to register. The cloud was there, in front of every star. You did not see it. You never will. The Oort cloud is not out there. It is all around us. It always has been. This is, in some sense, the most quietly humbling fact about our place in the universe. We are not even where we think we are. We are surrounded by a structure so large that it makes the orbits of all the planets look like a dot. And the structure is mostly invisible, mostly silent, mostly undisturbed, drifting in deep cold, waiting for the slow processes that will, occasionally, send some piece of it falling toward us. There is something out there. We will probably never see it, but we know it is there. The Oort cloud has been with the Sun for the entire history of the solar system, about 4.5 billion years. From very nearly the beginning, when the planets were just finishing forming and the early gas giants were flinging icy bodies outward, the cloud has been in roughly its current configuration. The objects have drifted. Individual ones have been knocked loose. New ones have occasionally been captured. But the overall structure has been stable. It will not always be stable. The Sun, like every star, is not eternal. It is currently in the main sequence phase of its life, the long, stable middle period during which it fuses hydrogen into helium in its core. This phase has lasted for about 4.5 billion years, and it will last for another 4 to 5 billion. After that, things will change. When the hydrogen in the Sun's core runs out, the core will contract under gravity. The contraction will release energy. The outer layers of the Sun will respond by expanding outward, becoming much larger and much cooler. The Sun will become what astronomers call a red giant. The red giant phase is dramatic. The Sun's radius will grow by a factor of about 200. It will swell to a size comparable to Earth's current orbit. Mercury will certainly be engulfed. Venus will probably be engulfed. Earth may or may not be engulfed, depending on the exact dynamics. Even if Earth survives the expansion, its surface will be heated to thousands of degrees. The oceans will boil away long before, the atmosphere will be stripped, and the planet will be left as a barren, blackened rock orbiting a dying star. But here is what is interesting for our purposes. The Oort cloud is so far from the Sun that the red giant phase does not directly disturb it, at least not at first. Even at the Sun's maximum red giant size, the cloud is still vastly further out than the Sun's outer atmosphere. The expansion of the Sun does not physically reach the cloud. There is no direct thermal effect that would melt or vaporize the icy bodies. What does change, however, is the Sun's mass. Throughout the red giant phase, the Sun loses mass. It sheds its outer layers into space as a slow, expanding stellar wind. By the time the red giant phase ends, the Sun will have lost roughly half of its original mass. The mass that remains will collapse into a white dwarf, a small, hot, dense ember about the size of Earth, slowly cooling. The Sun's loss of mass matters because gravity is what holds the Oort cloud together. The cloud is bound to the Sun by the Sun's gravitational pull. When the Sun loses half its mass, the gravitational pull on the Oort cloud is halved. Every object in the cloud, which was previously bound on a stable orbit, is suddenly held by a weaker force. The orbits, in response, change. Some objects, those that were on the most loosely bound orbits, simply drift away. They were already barely held. The reduced gravity is not enough to retain them. They float free, leaving the solar system entirely, becoming interstellar wanderers. Others, on more tightly bound orbits, remain in the cloud, but on larger orbits. They expand outward. The cloud as a whole becomes more diffuse, less dense, less tightly bound. This process happens slowly, over hundreds of millions of years, as the Sun gradually loses its mass during the red giant and subsequent phases. By the time the Sun is a white dwarf, a stable, cooling ember, the Oort cloud will have lost a significant fraction of its objects, and what remains will be much more diffuse than it was before. But that is only the beginning of the unraveling. After the Sun becomes a white dwarf, the Oort cloud, what remains of it, continues to be disturbed by the same forces that disturbed it before. The galactic tide continues to act. Passing stars continue to make occasional close approaches. The combination of these forces continues to nudge objects loose. Over billions of years, slowly, the cloud is eroded. Object by object, the cloud's residents drift away. Some go inward, falling toward the white dwarf, or being ejected after close approaches. Most go outward, into interstellar space, becoming part of the broader galaxy. After 10 billion years of this, the Oort cloud will be mostly gone. After 20 billion years, almost entirely gone. After 100 billion years, completely gone. The cloud, which had been one of the largest structures in our solar system, will simply have dispersed. This is a long time. To put it in perspective, 10 billion years is longer than the current age of the universe. The universe is about 14 billion years old. The Oort cloud will take roughly that long to disperse after the Sun's main sequence, life, ends. The total span, from the formation of the solar system to the final dispersal of the cloud, will be something like 20 billion years, more than the entire age of the universe so far. By the time the Oort cloud has fully dispersed, the galaxy itself will look different. Stars will have moved. The Milky Way and Andromeda will have merged into a single galaxy, possibly called Milkomeda, possibly called something else by whoever names it. New stars will have been born from the gas of old ones. The configuration of nearby stars will be unrecognizable from anything we can see in the sky today. The Oort Cloud will outlast the Sun's main sequence life. The Oort Cloud will outlast the configuration of the local galaxy. The Oort Cloud will outlast every recognizable feature of the universe we currently inhabit. And then, slowly, it too will disperse. The ice, the carbon dioxide, the methane, the organics, all of the frozen chemistry that the cloud has been preserving for so long will become part of the interstellar medium. Some of it will eventually be incorporated into new stars and planetary systems. Some of it will be captured by other stars and become part of their own Oort clouds. Some of it will simply drift forever in the slow currents of the galaxy. This is, in its own quiet way, an act of redistribution. The solar system spent 4.5 billion years assembling and preserving the Oort cloud. The Sun's death and the long aftermath will spend tens of billions of years scattering it. The same material that built the cloud will eventually be returned to the galaxy. It is not a violent process. It does not look dramatic. It is just a slow, patient release. Object by object, year by year, million year by million year, the solar system will exhale everything it ever held. Some of what is released, when the cloud disperses, will continue to travel. Most of the Oort cloud objects, when they drift free of the Sun's gravity, will not be moving very fast. They were on loose, slow orbits to begin with. When they break free, they move at speeds of perhaps a few hundred miles per hour relative to the local interstellar medium. That is not fast. It is, in fact, much slower than the typical motion of stars in the galaxy. They will not travel far on galactic timescales before being captured by some other gravitational influence. Some will be captured by other stars, becoming part of those stars' Oort clouds. The exchange we talked about earlier between our cloud and the clouds of nearby stars accelerates dramatically once the Sun's gravity weakens. Material that has been ours for 4.5 billion years will become someone else's. Some will simply drift on long, slow trajectories through the spaces between stars. They will pass through other systems occasionally. Sometimes they will be captured. Sometimes they will continue on. Over hundreds of millions of years, they will spread out, distributed across the galactic disk, no longer associated with any particular star. And some of them, on rare occasions, may fall into the inner regions of other planetary systems. Some of them may, on even rarer occasions, encounter planets. The chemistry they carry, the water ice, the organic molecules, the amino acids, the precursors to life, may be delivered to other worlds. We will not be there to see this. We cannot know whether anything will come of it, but it is possible. The chemistry of life, frozen for billions of years in our Oort cloud, may eventually fall on a warm world somewhere, far from here, billions of years from now. If such a thing happens, the chemistry of our cloud may continue. The patterns we contain, the molecules we have preserved, may become part of a new biology, in a place we will never know. The cloud will have, in some indirect and probably unobservable sense, succeeded at something. It will have carried its inheritance forward into a future that no one in our solar system was around to witness. This is speculation. It may not happen. The chemistry of the cloud may simply disperse, never landing anywhere useful, never participating in anything new. The materials may be too dilute, the distances too great, the probabilities too small, but the materials are there. The clouds of other stars are also there. The galaxy is full of this slow, frozen architecture. And the architecture is exchanging material, slowly, all the time, in directions that lead to outcomes we cannot predict. Let us close with one specific image. Somewhere in the Oort Cloud right now, there is an object that will be the last comet ever to fall toward our sun. We do not know which object it is. We will never know. But it exists. It is somewhere in the cloud, drifting on a long, slow orbit, doing what it has been doing for the past 4.5 billion years. At some point, perhaps 100 million years from now, perhaps 1 billion years from now, perhaps later, this object will be disturbed. A passing star, or the galactic tide, or some other gentle force, will give it a small nudge. The nudge will be enough to send it falling inward. It will fall for a very long time, thousands or millions of years. During this fall, the sun perhaps will still be relatively normal. There may still be planets. There may still be life on Earth, or on something descended from Earth, or on some other world that humans in some form have come to call home. There may not be. We cannot predict. But the comet will fall. It will warm up. It will develop a tail. It will cross the orbit of Neptune. It will cross the orbit of Saturn, of Jupiter, of Mars. It will cross the orbit of Earth, perhaps, and either pass quietly or, in some less likely scenario, strike something. Either way, eventually, it will reach the sun. It will swing close in the long, intricate dance that comets perform when they fall all the way inward. Its tail will be long, perhaps spanning across the visible sky. If anything is alive to see it, the sight will be beautiful. Then it will swing back outward, and slowly, over thousands or millions of years more, it will return to the cloud, or be ejected entirely, or be destroyed by the sun's heat. Whatever its fate, it will be the last of its kind. After it, no more comets will fall. By that point, the sun will be in its final stages. The Oort Cloud, what remains of it, will be too diffuse to produce comets in any significant numbers. The dynamics that produced comets for billions of years will have ended. Imagine that last comet's journey in detail, even though we will never see it. It will spend most of its existence in deep cold, far from any light, at the outer reaches of a cloud that is itself in slow dispersal. Most of its companions will have been lost long before, drifting away as the sun's gravity weakened. The last comet will be one of the few remaining. It will not know. It is one of the last. It will not know anything. It will simply be there, on its slow orbit, doing what gravity tells it to do. Then, at some point, the perturbation will come. Some passing star, some final tug from the galactic tide, some last gravitational disturbance, and the comet will fall. It will fall for an enormous span of time, slowly accelerating, slowly warming as it approaches the dim white dwarf that the sun has become. By that point, our sun will not be much of a sun. It will be a small, hot, fading ember, surrounded by whatever planets survived the red giant phase, all of them dark and cold. The comet will still fall. Its ice will still vaporize as it approaches. It will still develop a tail, though the tail will be shorter and dimmer, illuminated by the much weaker light of the white dwarf. The display will be smaller than the comets we see today. But it will still be a display, a last gesture from the cloud, a final visitor. And then, the cloud will be too sparse to produce more. The era of comets will be over. The cloud will continue to disperse, slowly, for billions more years. But the great visitors, the long-period comets that have been part of the Sun's history since the beginning, will be gone. Every comet we have ever watched, every streak of light our ancestors feared, every tail of ice that has burned across our sky came from the Oort Cloud, from the very edge of everything we belong to. It fell toward the light. For a brief moment, we saw it, and then it returned to the dark. There is a comet somewhere in the cloud right now that will be the last. There are others that will come before it, many of them. We will watch them fall. We will not know which one is the last when it comes. We will only know, much later, looking back at the geological record, that no more came. By then, there will be no one to look. Out there, right now, trillions of objects wait in perfect silence. They have waited since the beginning of the solar system. Most will wait until the end. Some will fall. We will watch them fall. We will not know their names, and they will not know ours. The Oort Cloud is real. The objects are real. The distances are real. The fact that we cannot see them does not make them less real. It makes them stranger, perhaps, more worthy of slow contemplation, more worth thinking about. On a long evening, when the sky is clear and the stars are out and you remember, suddenly, that the stars are not the whole story, that between every star, around every star, there is something else, something colder, something darker, something we have only ever guessed at, but which is there, undoubtedly there, holding the slow chemistry of the early universe in its long, patient orbit. The cloud is the silent backdrop to everything we have ever done. There is something gentle about that. The cloud does not threaten us most of the time. It is too far away, too thinly populated, too quiet. It does not interfere with our daily lives. It does not affect the seasons or the tides or any of the rhythms we live by. It is simply there, far above, surrounding everything we know, holding its small frozen objects in patient suspension. When you go outside tonight and look up at the sky, you will not see the Oort Cloud. You will not be able to see it. The instruments humans have built are not capable of resolving it, and probably never will be in any meaningful sense. The cloud's objects are too small, too cold, too distant. They emit no light. They reflect almost none. The sky, from any point on Earth, looks empty between the stars. But it is not empty. Between every star you see, in the space behind them, around them, between them, the clouds of those stars are there, holding their own ancient ice in their own slow orbits. Multiplied across 200 billion stars, the galaxy is mostly this. Mostly the dark, the cold, the slow, the unobserved. Somewhere, on a planet around another star, perhaps, there is a being looking up at its sky tonight, watching its own stars. Around that being, invisible, is the cloud of its own sun, made of the same kind of frozen chemistry as ours. The being does not see it. The being is inside it. The being has always been inside it, for the entire history of its species. This is, perhaps, the most universal thing about us. Not the planets we orbit, not the chemistry we are made of, not the stars we look up at, but the slow, dark architecture that surrounds every star, that fills the spaces between, that holds the inheritance of the early universe in patient cold. We are inside one of them. They are inside theirs. It has been here longer than the Earth. It will be here longer than the Earth. It is most of what is. And yet, somehow, impossibly, by the patient work of human reasoning, across centuries, we found it. It does not know we are here. It will never know. But we know it is there. That is enough.